Hello friends, in the previous lecture you have seen the definition and example of cosets. So here in this lecture we are going to continue cosets, but here we are going to see some properties of cosets. So as you know, the cosets are of two types, left cosets and right cosets. Left coset means the element of the group G are multiplied from the left, then that is your left coset, and if you are multiplying elements of the group from the right hand side, then that will give you the right coset. So there is no much difference between left coset and right coset, and we will see these properties here, so how they are related. So let us take a group G, and H is a subgroup of this group G, and suppose that A and B are two elements of D. Then the first property says that the representative element of a coset, and so here we are going to take left cosets. So if you are taking left coset AH, then this A is called the representative element of this coset. So this property says that the representative element belongs to the cosets. So we are going to show that how this A belongs to AH. As you know that elements of AH are of type A into H, where H is the element which is coming from this subgroup. So if you want to show that A belongs to AH, that means we have to show that A can be written as A into some element of capital H. So let us see, this is just a one line proof. So we know that A can be written as A into identity, because identity H is a subgroup, so identity belongs there. So we can multiply A with identity. So A can be written as A into identity. So this AE belongs to AH. That means this becomes as a member. This becomes as a this becomes in the form of an element which belongs to this left coset AH. So A is equal to AE and AE belongs to AH. So A belongs to AH. That means the representative element belongs to the coset. Similarly, you can prove for the right coset also. Then you will write A as E into A. Then that will belongs to H. So this is your first property. Now second property. So second property says that AH is equal to H if and only if A belongs to H. Your left coset AH will be equal to H if this representative element is in H. So let us prove it. We're going to prove it both ways. So first suppose that AH is equal to H. So we have to show that A belongs to H. So if AH is equal to, by in the first property we have already shown that A belongs to AH, and AH is equal to H is given. So that means A belongs to AH is equal to H. So this implies that A belongs to H, and so we are done. Now converse. Suppose that A belongs to H, then we have to show that AH is equal to H. So if I prove that AH is a subset of H and H is a subset of AH, then we are done. So let us try to do that. This is the definition of AH. How do we write this left coset AH? So this will be a set of this type AH such that H belongs to H. Now, since A and H both are in H, therefore by closure property, we can say that A into H belongs to H. So AH belongs to H. So we were taking an element AH, and we are AH was in this question. So AH belongs to AH here, and now we have shown that AH belongs to H. That means AH is a subset of H. Every element of AH is in H. That means AH is a subset of H. Now, conversely, we will prove that H is a subset of AH. So let H is some element of this subset, this subgroup H. Since A belongs to H and H also belongs to H, so, and H is a subgroup, you know. So if some element is in H, then its inverse is also in H. So A inverse exists in H. Then by closure property, if A inverse belongs to H and H belongs to H, then their composition also belongs to H. So A inverse into H belongs to H. Thus, H, which can be written as identity into H, this will be equal to, identity can be written as A into A inverse. So this will be A inverse into H. Then by associative property, you can just write it like this, A into A inverse H. And your A inverse H belongs to H. Here we have already shown that A inverse H is a member of capital H. So this H can be, this H we have written as A into some element of H. That means this belongs to AH. So H belongs to AH. So H, which was a member of capital H, here we have shown that it belongs to AH. So this was any arbitrary element. That means every element of H is in AH. That means capital H is a subset of AH. So this property we have proved that AH is equal to H if and only if A belongs to H. So if your representative element A is coming from the subgroup, then your the coset, left coset becomes equal to the sub. So this is an important property that you will see from examples also. Now this third property. So this is very important. This says that you have two left cosets A and H, AH and BH. So AH is equal to BH. That means the two cosets AH and BH, they are same. They are exactly equal. AH is equal to BH or AH intersection BH is equal to phi. That means either they are equal or they are disjoint. There is nothing common between them. We can also state this property as prove that any two left cosets of H in G are either identical or disjoint, H being a subgroup of G. Or we can say that HA, this is for right coset. So this was for left coset. Now the same result is written for right coset. HA intersection HB is equal to phi or HA is equal to HB. That is, any two right cosets of H and G are either identical or disjoint. So, if you remember in the last lecture, we have already shown when we were talking about the left cosets uh, of H in S3, when we were talking about cosets of a subgroup of S3, the symmetric group. So there we have seen that how two cosets were same and their union was coming equal to the group. So you can see that previous lecture from the channel to know more about that. So let us come back to this result. This result says that if you have any two left cosets of H in G, then either they are same or their intersection is empty. So let us prove it. So first suppose that HA intersection HB is phi. There is nothing common. So if their intersection is empty, the two right cosets HA and HB have no element in common. That means we are done. There is nothing more to do here. So next, suppose that their intersection is non-empty. There is something common between them. So in that case, we are going to show that HA is equal to HB. So if their intersection is non-empty, that means there is some element which belongs to the intersection. So suppose that C belongs to HA intersection HB any element. So if C belongs to HA intersection HB, that means C belongs to HA and C belongs to HB both. So if C belongs to HA, then C can be written as H1 into A for some H1 belongs to capital H, and if C belongs to HB, then C can be written as H2 into B for some H2 belongs to capital H. So this is also equal to C and this is also equal to C. That means H1A is equal to H2B. And this implies that, so if you multiply H1 inverse on the left hand side, on the left side, on both the sides, if you multiply H1 inverse, then you will get H1 inverse H1A. That is, this will be your identity into A and identity into A will be A. So directly I have written it as A. So A is equal to H1 inverse H2B. And if you multiply H2 inverse on both the sides, then you will get B is equal to H2 inverse H1A. So suppose this is 1. Now let X be any element of HA. So if X is in HA, then X can be written as H into A for some H belongs to H. So X is equal to HA, then substitute the value of A from here, then HA will be equal to H into H1 inverse H2B. So take all these H together. So they all are members of the subgroup H. So this H1 inverse H2, this by closure property, this will be a member of capital H. That means X belongs to HB. So X was in HA and we have shown that this belongs to HB. That means HA is a subset of HB. So this is your 2. Now, conversely, suppose that y is some element of HB. So if y belongs to HB, then y can be written as H dash into B for some H dash belongs to capital H. Now by 1, in 1 you have values of A and B. So first we have used this value of A. Now we are going to use B. So y is equal to H dash B. Then this can be written as H dash into H2 inverse H1A. So this, all these H, they are coming from capital H, this subgroup. So by closure property, their product will also belong to capital H. This implies that Y belongs to HA. So Y, which was coming from HB, we have shown that it belongs to HA. That means HB is a subset of HA. So from 2 and 3, so in 2 we have shown that HA is a subset of HB. And in 3, we have shown that HP is a subset of HA. So from 2 and 3, HA is equal to HP. Similarly, you can prove the same result for left cosets. If you take two left cosets AH and BH, then either AH intersection BH is equal to 5 or AH is equal to BH. So whenever you are trying some example related to cosets, you are finding some cosets, then you can observe this property that two cosets may be equal, and they may be the case when there is nothing common between the cosets. So that was one of the important property cosets. In the fourth property, we are going to show that you have two right cosets HA and HB. Then this property says that HA is equal to HB if and only if A into B inverse belongs to capital H. So we have A can be written as E into A. So this belongs to HA. Therefore, A belongs to HB implies that A is equal to H into B for some H belong to H, because HA was your HB. Here we have HA is equal to HB and we are proving that A into B inverse belong to H. So HA is equal to HB. Here we have used this fact. A belongs to HA and HA is equal to HB. That means A belongs to HB also. And A belongs to HB implies that A can be written as H into B for some H belongs to H. So this implies that A into B inverse is equal to H. If you multiply B inverse on the right, from A B will multiply by B inverse on both the sides, then A into B inverse will be equal to H, and H belongs to capital H. That means AB inverse belongs to capital H. So this part is done. Now conversely, now suppose that A into B inverse belongs to capital H. Now we have to show that H is equal to HB. So if AB inverse belongs to capital H, that means AB inverse can be written as H1 for some H1 belongs to capital H. So from here, A can be written as H1 into B multiplied by B on both the sides. You will get this. Now let X belong to HA. So you have to show that HA is equal to HB. That means you have to show HA is a subset of HB and HB is a subset of HA. So first we are trying to show that HA is a subset of HB. So if you want to show that HA is a subset of HB, then you have to take some element of HA and then prove that it belongs to HB. So let X belong to HA. This implies that X can be written as some element of H into A. So that element we have supposed that is H2. So X is equal to H2 into A for some H2 belong to capital H. This implies that X is equal to H2 into H1B, where A was H1 into B, that we have used here. So H2 into, by associative property, you can write this as H2 H1B. So this, by closure property, this belong to capital H. That means your X is belonging to HB. So it was from HA and we have shown that it belonged to HB. That means HA is a subset of HB. So this is your one. Now we are going to prove that HB is a subset of HA. So now suppose that X is some element of HB, then X can be written as H3 into B for some H3 belongs to capital H. So this is equal to H3 into, so value of B can be written here H1 inverse A. So now by associativity, you can write it as H3 H1 inverse into A. And this is by closure property, this belongs to capital H. So your H belongs to HA. That means HB is a subset of HA. So this is your 2. Now 1 and 2 imply that HA equal to HB. Similarly, same result you can prove for left coset also. AH is equal to BH if and only if A inverse B belong to capital H. So this was also a good property, an important property. Now this is fifth property of cosets. So here also we have two cosets, two left cosets AH and BH. This property says that order of two left cosets is same. That is, the number of elements in the left coset AH is same as the number of elements in the left coset BH. That means we need to show that there is a one-to-one correspondence between any two left cosets of H and G. One-to-one correspondence, that means we have to show that there is one-one-on-two mapping between two left cosets. So suppose that AH and BH are two left cosets of H and G. So here A and B are elements of G. Now we are required to show that there is a one-to-one correspondence between AH and BH, or there exists a one-one-on-two mapping between AH and BH. So for that we have to define a mapping. So define a mapping phi from AH to BH as phi of AH is equal to BH for every H belongs to H. So first we have to show that phi is 1. After that we will show that it is onto also. So to prove that phi is 1, suppose that phi of AH1 is equal to phi of AH2. So from this definition, phi of AH1 will be BH1. So this implies that BH1 is equal to BH2, and this implies that H1 is equal to H2. By left cancellation law, this becomes H1 is equal to H2. So this implies that AH1 is equal to AH2, and thus phi is 1 to 1. Now we have to show that phi is onto. So your phi was from H to BH. So if you want to show that phi is onto, that means you have to prove that for every element here there exists a pre-image here. So let y belongs to BH be any element. So if y belongs to BH, that means y can be written as B into H for some H belong to H. Y is equal to BH. So from this definition of phi, from this phi of H is equal to BH. So you have taken BH. This y is equal to BH. That means this implies that y is equal to phi of AH by 1. This implies that, so if you suppose that AH is some x, so this implies that y is equal to phi x, where x is equal to AH and AH belongs to this capital AH. So y, you have written y as phi of x. X is coming from AH, and hence phi is onto. Hence there is a 1-1-1-2 correspondence between AH and BH. And if there is a 1-1-1-2 correspondence, that means there are same number of elements in those cosets. So order of AH is same as order of BH. Same result can be proved for right cosets also. Order of right coset HA is same as order of right coset HB. So order of two cosets to left cosets is same, or order of two right cosets is same. Now this is property number 6. It says that HA is equal to AH. That means the left coset is equal to right coset if and only if H is equal to AH, A inverse. So AH is equal to HA. If and only if AH, so you just multiply A inverse from the right and on both the sides. So AH A inverse will be is equal to HA A inverse. then this is possible if and only if AH A inverse is equal to HA A inverse. By associativity, you can write it like this: A into A inverse, and A into A inverse is your identity. So this is equal to HE, and HE is equal to H. So this is possible if and only AH A inverse is equal to H. So this is the simple proof. AH is equal to HA if and only if H is equal to AH A inverse. Now number 7. So this is the last property. This says that the left coset AH is a subgroup of G if and only if A belongs to H. So if your representative element belong to the subgroup, then your coset, the left coset AH becomes the subgroup of group and converse also. So AH is a subgroup of G if and only if A belong to H. So suppose that AH is a subgroup of G. So if AH is a subgroup of G, that means identity belongs to AH. If it is a subgroup, then it has all the properties of the group. So identity should be there. So identity belongs to AH. So this implies that AH intersection EH is not equal to 5, because identity belongs to AH and identity belongs to EH also. That means their intersection is non-empty. That means by property number 3. So let us see what is property number 3. We have proved. So this is your third property. So property third says that two cosets AH and BH, either they are same or there is nothing common, their intersection is empty. So if their intersection is non-empty, that means they have to be same. So we are on property 7. Yeah, this. So H intersection EH is non-empty, then by property 3, AH is equal to EH and EH is your H, so AH is equal to H. So this implies that A belongs to H. By property 2, we know that the representative element belongs to the coset, so A belongs to AH and AH is equal to H, so A belongs to H also. So this we are done. Now converse. Let us see that converse part. So let A belongs to H. Then again by property 2, AH is equal to H, and H is a subgroup of G. That means AH is a subgroup of G. So this is an interesting property. AH is a subgroup of G and only if it belongs to H. So these are some of the important properties related to cosets that we have seen here in today's lecture. So let me just revise these properties again for you. So first we have seen that the representative element of a coset belong to the coset. Then in property 2, we have proved that AH is equal to H. That means the coset becomes equal to the subgroup. The left coset AH is equal to H if and only if A belongs to H. If your representative element is coming from the subgroup, then your coset is same as the subgroup. So if you know that the element is coming from the subgroup, then there is no need to calculate your coset. You just directly you can write coset as same as the subgroup. Now third property says that if you have two cosets, then either they are same or their intersection is empty. This is also an important property. Then in the next property, we have proved the fact that HA is equal to HP. Two cosets are equal if and only if A into B inverse belongs to H. So after that, you have seen that order of two left cosets is same, or you can say order of two right cosets is same. Now property 6 says that AH is equal to HA. When do we say that the left coset is equal to right coset? So the left coset AH is same as the right coset HA if and only if H is equal to AHA inverse. Now property 7, you have seen that AH is a subgroup of G if and only if A belongs to H. So these are the some of the important properties of cosets. So in our next lecture, we are going to see the Lagrange's theorem. So these properties were very important before doing Lagrange's theorem. So That's why I have given you all these properties and their proofs. So uh, after these properties of cosets, understanding Lagrange's theorem would be very easy. So in the next lecture, we are going to see the Lagrange's theorem. Till then, bye bye, take care.